Hi, my name is Farzan Debashi. Welcome to our virtual talk at MobiCom 2021. This is a joint work with my colleagues Ali, Tim, and Omid. In this talk, I present our verification paper, which is a try to answer if Wi-Fi backscatter systems can replace RFID. The RFID technology has been around for more than 2 decades. RFID tags are cheap, tiny, and battery-free. So this technology is great, but why don't we see this technology everywhere? It is because RFID readers are bulky and expensive. So researchers have introduced Wi-Fi backscatter technology to use existing Wi-Fi infrastructure to read battery-free tags. But the question is, can Wi-Fi backscatter technology really replace RFID? We tried to address this question by comparing different Wi-Fi backscatter technologies to each other and RFID. We have got two types of Wi-Fi backscatter systems. Out-of-channel systems like Hitchhike, FreeRider, or MobiCom, and in-channel ones like Wi-Fi backscatter, which actually is the name of a system, and WiTag. First, out-of-channel Wi-Fi backscatter systems. In these systems, client sends an excitation signal in channel X, and tag reflects its received signal into an adjacent channel Y. Then another AP decodes data in channel Y. Later on, by comparing the data received from channel X and Y, the system would be able to decode tags data. Since a battery-free tag cannot perform channel sensing before transmission, it causes interference for other devices on channel Y. In in-channel Wi-Fi backscatter systems, a tag reflects its signal in the same channel as the excitation signal. This creates less interference for other channels compared to the out-of-channel competitors. Although in-channel systems only make use of a single channel which is reserved by the client, they still suffer from the interference problem. This is due to their nature, since they naively change all Wi-Fi channels during their transmission. To quantify Wi-Fi backscatter interference, we use two Wi-Fi networks. First, a backscatter Wi-Fi network, and second, a neighboring Wi-Fi network. These two are separated by a wall. The backscatter Wi-Fi network, as shown in the green box in the figure, consists of a Wi-Fi transmitter, a receiver, and a backscatter tag. The neighbor network consists of a Wi-Fi transmitter and a receiver. As shown in the figure, we call the distance of the transmitter and receiver of the neighboring network to be D1, and the distance between the Wi-Fi backscatter system and the transmitter in the neighboring network to be D2. The figure shows the results of such experiment. We see that the neighboring network can achieve up to 100 megabit per second when the backscatter tag is inactive. However, when an out-of-channel tag becomes active, the neighboring network experiences more than 70% drop in its throughput. This means that out-of-channel Wi-Fi backscatter systems can significantly impact the performance of other nearby Wi-Fi networks. We now evaluate the impact of in-channel backscatter tags on other Wi-Fi networks. This is similar to the previous experiment, except that the tag does not shift the signal to an adjacent channel. However, as mentioned earlier, because the tag changes its reflecting state, it potentially impacts all Wi-Fi channels. As shown in the figure, this type of Wi-Fi backscatter systems has less impact on performance of other Wi-Fi networks. In particular, the throughput is dropped only about 30% in most cases. The negative impact of these systems is more subtle because of two main reasons. First, the oscillators used in in-channel Wi-Fi backscatter systems do not operate at high frequencies. Hence, they do not move or leak any signal to adjacent channels. Second, in-channel Wi-Fi backscatter systems cause interference only if they backscatter the neighbor's signal. In fact, this is actually why when D2 is very small, the impact on the neighbor network is worse. Now let's conclude advantages and disadvantages of different Wi-Fi backscatter systems. In-channel systems such as Wi-Fi backscatter and WiTAG consume considerably less energy since they operate at lower frequencies and they do not need power-hungry oscillators. In terms of throughput, Hitchhike outperforms its competitors. The line-of-sight range of Hitchhike and FreeRider are longer than other systems. Speaking of interference, all systems are not that great, but as we elaborated before, in-channel Wi-Fi backscatter systems do a better job. So far, we have evaluated and compared the performance of different Wi-Fi backscatter systems. Now let's get into answering the main question we asked ourselves. Can Wi-Fi backscatter systems really replace RFID systems? To come up with an answer, we picked a Wi-Fi backscatter and compared it to RFID systems. We chose WiTAG, since it does not need any hardware modification to existing Wi-Fi infrastructure. Then we compared it with a typical commercial RFID system in terms of energy harvesting, throughput, range, and scalability. To compare practicality of Wi-Fi backscatter and RFID, we measure the total amount of energy available for RF harvesting at a variety of distances for both Wi-Fi and RFID systems. To do so, we measure the power of the RFID signal at different distances that range from 1 to 7 meters from the reader's antenna. Then we repeat the same process using a Wi-Fi access point. This graph depicts the results of this experiment. The figure shows that for a given distance, the RFID reader offers more energy to tags. Therefore, to enable battery-less communication, RFID tags operate at longer distances. This is because Wi-Fi signals have much higher frequencies and hence experience higher path loss. However, RFID uses directional antennas, so this amount of power is available only in front of the antenna. Whereas for Wi-Fi, the power is available in all directions because Wi-Fi uses omnidirectional antennas. Next, we compared the throughput of WiTAG and RFID. To have a fair comparison, we tried to saturate the length in both cases. To do so, we used as many as 150 RFID tags. We picked this number based on our experiments. And in the Wi-Fi side, we programmed WiTAG to send packets back to back to ensure saturation. Then we put RFID tags at different distances from 1 to 6 meters away from the reader's antenna, and we measured the total throughput. We then repeated the same process using WiTAG. This graph shows the throughput of RFID in blue and WiTAG in red at distances ranging from 1 to 6 meters from the antenna. It can be seen that RFID always maintains a considerable advantage in terms of throughput compared to WiTAG. We hypothesize that this is because RFID systems send multiple bits per single packet. whereas WiTAG is capable of only sending a single bit per subframe. This shows the importance of development of a more mature protocol for systems like WiTAG. Now let's compare the communication range of RFID with WiTAG. To measure the range of the RFID system, we place the RFID reader at a fixed location and a tag in front of it. We then move the tag away from the reader while the reader sends queries to the tag. We measure the distance at which the reader stops receiving any response from the tag. We repeat this experiment for 3 different types of tags using 2 different scenarios. First, line of sight, and second, non-line of sight, where the tag is inside of a box made of cardboard. We then repeat this experiment using WiTAG. In this graph, we see the results of the range experiment. In the left side, we see the range of RFID tags, which is around 5 to 13 meters in line-of-sight scenarios. The right side of the graph shows the WiTAG range when the device is placed at 6, 8, or 10 meters away from the access point. Overall, the RFID wins this comparison by large margins, not only because of its directional antennas, but also due to the lower frequency used by the technology. Use of specific designed Wi-Fi backscatter antennas may increase the range of Wi-Fi backscatter systems in future. We now compare how the throughput of WiTAG and an RFID system change as the number of tags increases. We place an increasing number of tags 1 meter away from the reader's antenna and measure the total number of packets read per second across all tags. Then, to evaluate WiTAG's operation, we develop a simulation. The figure shows that although WiTAG scales well up to 10 tags, its performance degrades when there are more than 10 active tags. When the number of tags increases, the number of successful packets starts to decrease due to higher probabilities of concurrent transmissions that results in collisions. In contrast, the total number of successful packets increases for the RFID tags because their MAC layer protocol avoids collision. So in this factor, RFID beats Wi-Fi backscatter technology again. We showed that out-of-channel Wi-Fi backscatter systems cause significantly more interference compared to their in-channel competitors. In this paper, we compared different Wi-Fi backscatter systems in terms of their power consumption, throughput, range, and interference. We then compared these systems with RFID in terms of energy harvesting capabilities, throughput, range, and scalability. To conclude, we should say that Wi-Fi backscatter systems are still on their way.